So this is the first problem of today's Div 3. And in this problem, we're given that there is an array A of n integers, and we must perform the following two operations. And in this order only, at like the first operation and then the second operation. So these operations are that first operation is we can arbitrarily rearrange the elements in any order, or we can also leave the order unchanged. And the second is we can choose any subarray of this array, like any contiguous segment of the original array, and reverse the, like assign them. AI can be assigned minus AI. So that means just reverse their value, like reverse their sign. If it's positive, make it negative. If it's negative, make it positive. So we have to find the maximum sum of the array elements. So let me explain this here. So see, we have to perform two operations, right? And the first operation is that, let's say this is the array. So we can rearrange, like we have the choice. Let's say there was a negative element here, negative here, negative here. So what we can do, we can just combine, like let's just combine these, like club these three together, and after that the remaining elements. And later on we can choose our LR like this and just switch the sign of these, right? So let's take an example. So let's take the first example. The first example is -2, 3, and -3. And by the way, the first and second are both optional moves. Like in first move, you can choose to not, like choose to go with the initial arrangement only. And in the second move also, you can, like instead of like choosing an L or R, L and R, you can just not choose L and R and like keep the elements like they are. So let's say this is the example. So in this, we can club -2 and -3 together, and this is the positive element. So we'll choose our L this, R this, and just convert these negative elements to positive elements. So our array will become 2, 3, 3, and the final sum will be 8. So in this problem, like what we have to do, just see, even if the element is positive, it is going to come like that only in sum. Otherwise, if the element is negative like these, we'll club them and make them positive. So if your value is positive or negative, it is going to contribute in your sum. Its absolute value will always contribute. So just take your array A as input, then for every value find, like add the absolute value of that thing to your answer. Is it clear? Yes, no. And why this is true? Because like this thing, we can club the negative elements because we can rearrange them in any order. And if there are no negative elements, then don't do anything. Just take the sum, and that is the maximum value that you can get. Is this clear to everyone? Okay. So let me show you the implementation. So this is the implementation. In this, I have first taken the number of test cases as input. Then I have taken this number of array elements as input, the size of array, then all the array elements, and finally, I'm just adding the absolute value of each element to my answer and printing it. So hopefully this implementation is also clear, right? Or is anyone having any doubt?
Clear.
Okay. So let's go to the next problem. So in this next problem, we're given that we have an array A, and in one move we can perform either of the following two operations, and we can perform any number of moves. So either we can choose an element from an array and remove it, or choose an element from the array and increase its value by 1. So we have to find the the minimum number of moves such that the sum of the array elements is divisible by 3. So let's take this example. Let's take 2254 first. So what is the sum of this? 13, right? So 13 is not divisible by 3. So let's say either what I can do, I can increase this element by 1 in one move, so that sum will be 14. Still the sum is not divisible by 14. I can do one more operation and add 1. So by doing two operations like this, my sum will be 15 and this is divisible by 3. Or a better way is just remove this 2. Like do the first operation and then your sum will become like these are the remaining elements and your sum will become directly. Should we remove this 2? What will be the sum? We'll get 11. 11 is also not divisible. So let's say we remove this 4. If we remove this 4, then these are the remaining elements and now the sum will be 9. And 9 is divisible by 3. So in one operation only, like in one operation only, we can just remove this and our sum will be divisible by 9. So that's why the answer for this is 1. Is it making sense? How did we get 1? So let's take another test case also. Let's say 5, 5. So we have 10 as the sum. So either we can add 1, we'll get 11, then again add 1, we'll get 12. So 12 is divisible. If we decided to remove, let's say we removed 5, the remaining element is 5 and the sum is also 5, not divisible. We'll have to remove this also. Now there is no element, so the sum is 0 and 0 is divisible. So this way also it's 2 moves, this way also it's 2 moves. So for this 5, 5, the total number of moves to get the sums divisible by 3 is 2. Is it clear? Okay. So now what we are actually doing, see, there are 3 cases. Broadly speaking, first of all, there are 2 cases. Either the total or the sum divisible by 3 is equals to 0, or sum divisible by 3, like sum is not divisible by 3. Here the sum is divisible by 3 or the sum is not divisible by 3. So in this case, the number of moves, minimum moves is 0 directly. In this case, either sum divisible by 3 is like sum remainder 3 modulo 3 is either it's 1 or 2. In this case, if we decided to go using addition, we'll have to do 2 operations. Right? In this, like additions, I'm saying like we'll choose any element and we'll add, like we'll do 2 operations. In one operation, we'll add 1. In another operation, we'll add 1. So 2 operations. In this, if we go according to plus, like for second move, we'll have to do 1 operation. So in this, what we can do, we can also check if we have an element in the array for which that element modulo 3 is equals to 1. If this is true, in this case, then by removing, I can get 1. In one operation, I can get the sum divisible by 3. Right? Yes, no? In this also, like if there is an element for which element modulo 3 is equals to 2, then also in this, if we decided to go along this way, then also one operation is required. So for this, when sum modulo 3 is 2, uh, like going along both these options gives me same value. But in this, if I remove, and like I can only remove, like it's only optimal to remove if my element modulo 3 is 1, then I'll get one operation. Because if let's say, see, there is, it's never optimal to remove an element for which you are getting, this is, because this is not optimal to remove because this won't change, sum modulo 3 won't change. And if you decided to remove elements for which element modulo 3 is equals to 2, for this kind of, like when your sum modulo 3 is 1, then you'll have to remove two elements, not one. You'll have to remove two such elements. So anyway, by adding also you will get like getting two moves. So that's why if you want something better, you need to remove an element for which element modulo 3 is 1. Then you'll get one operation. So is it yes, no? Is it clear? Yes, no, anything? Or is anyone having any doubt? Okay, so let me show you the implementation. So this is the implementation. In this, I have first taken n as input, then I have taken the array a as input. Then I have calculated the total sum. And if my total sum, like this is the value that I need to add first of all. This is like either you can write this using if else, or we can directly write this like this: 3 minus whatever is remaining. Like total modulo 3 is either 1, 2, or 3. 1, 2, or 0. If it is 0, this thing, the value inside bracket will be 3. And under modulo 3, you will get is at 0. So this is for that case only, under like this modulo 3. Otherwise, 3 minus total 3 is the value that you need to add to get to the total, to the next divisor of like a multiple of 3. See, if total modulo 3 gives you 1, you need to add 2 to any element, right? So that's why 3 minus total modulo 3. Otherwise, if total modulo 3 is 2, you need to add 1. So 3 minus total modulo 3 will give you 1. Now, I'm just counting how many elements in my array are such that under modulo 3, the remainder is 1, or under modulo 3, the remainder is 2. So just count 1 and 2. Now, finally, we can check if total modulo 3 is 1 and you have an element which is giving you 1 under modulo 3. So answer is minimum of answer or 1, because you can just remove this element. Otherwise, same thing for 2. You don't have to, like you can further optimize this, because but this is the general code and this will work for every case. Is it clear? Finally, we can print our answer. Like for in case of 2, you don't have to do this. If total modulo 3 is 2, from here only you will be getting 1. So there is no point of doing this. Is it clear? Yes, no? What about others? Okay, so let's go to the next problem. So in this problem, we are given that there are three positive integers, a, b, and l. And so it can be shown that there exists a way to choose non-negative integers k, x, and y such that l is equals to k multiplied by a to the power x and b to the power y. So our task is to find the distinct number of distinct possible values of k across all such ways. So this is a simple maths problem. Let me write the See, we are given three integers, L, A, and B. And it's is given that L is equals to K. So we have to find, see, X and Y can be varied, right? Accordingly, we have to find all distinct values of K. And looking at the problem constraints, we have A and B will be both between 2 and 100, and L will be between 1 and 10 to the power 6. So can someone tell me what is the maximum? Forget about Y. Let's say Y is 0. So L is K into e to the power x, right? Because something to the power 0 is 1. And let's say K is also 1. So L is equals to a to the power x. And L is, I'm taking L as maximum, 10 to the power 6. So a to the power x is a to the power x is 10 to the power 6. And let's take A as minimum. A as, like why I'm taking these values, I want to find what is the maximum value of x that can be. So A is 2. So 2 to the power x is 10 to the power 6. Is anyone having any doubt in this? Like I have to find what is the maximum value of x that there can be. Like in worst case scenario, what is the maximum x that I need to go for? Because eventually I'll plug values of x and y in this. I'll find the multiplication of this. And if this, like whatever the multiplication value is, whatever the product is, I'll divide L with this product. And if L is divisible by this product, I'll have a value of k with me. Like upon dividing L with this product. But up till where do I need to go? So if you find this, x will be nearly 20. Like 2 to the power 20 is more than 10 to the power 6. So there is just like how many distinct values of x do you need to check for? 20 distinct values. That is 0, 1, 2, all the way up till 18, 19. So these are the distinct values of x that you need to check for. Why? Because a is either 2 or more. If it is more, then you'll have to like don't even go up till here. Yes. Okay. So if we, by the same logic, that if x becomes more than 20, then a to the power x is definitely more than 10 to the power 6. So by same logic, if y becomes more than 20, b to the power y will be more than 10 to the power 6. So y, what is the range for like valid values of y? It's between 0 and to 19, including 0 and 19, right? So we have 20 possible values of y and 20 possible values of x. We had this equation L k multiplied by a to the power x b to the power y. So x is like there are 20 possible values, and for y also there are 20 possible values. L is fixed, a is known, b is known. So we need to plug, like there are 20 distinct values that we can plug here, 20 distinct values that we can plug here, and find the product of this. Check if L is completely divisible by this thing or not. Why? Because if L is not divisible by this product, this simply means K cannot be a floating point number, right? So K needs to be an integer. So that's why just check if this is a like L modulo this product, this thing is equals to 0. If it is, just like L divided by this product is one of your possible values of K. Now you cannot just keep counting like this, because you need just distinct values. So whatever the value of k that you're getting from here, you can insert it in a set. Like insert all the valid values in a set, and finally your answer is the size of this set. Why you need to use a set? Because you need distinct values. And why is this optimal? Because how many, at max, how many distinct values will be there? Can anyone tell me? What is the maximum number of distinct values? Can I mean, like, anyone give me an upper bound? 400, right? 20 times 20. Like, let's say for each and every possible value for this, you get this thing. But actually, it will be much, much, much lower, because you are like, when we say 20 into 20, we are considering something like 2 to the power 20 into 2 to the power 20. This is 10 to the power 12, more than 10 to the power 12. And L is 10 to the power 6. So it will be much, much less than 400. So, but what is like, set can easily take this much, right? You won't have, you don't need to consider about the log n factor or anything. Is it clear?
Yeah, but how to find a to power x like
Yes,
in efficient way? A
yes,
is
yes, yes.
something very
Now,
we can
yes.
go to.
So see, here you can either use power function, but this is not efficient. Like, I actually covered this in level 1 or level 2 class. If you do this thing, this is actually why this is not like optimal to use here, because this is like, this gives you precision errors for bigger values. So instead of doing this, what you can do, you can have, let's say, val is equals to 1, and you need to iterate 20 times. So let's say you are iterating a loop using 20 times, because this is for x. Inside here, you will do the same thing for y also. But currently, I'm considering for x. So what you can do, you can multiply this val with a. And here you just need to also check one thing, that this value is less than L, less than or equals to L.
But like here constraints are low, so like that's why we can use power function.
Yes, you can, but still for some, like, this is a div 3 round, right? So right now, all the test cases, like, there is an open hacking round also. So you can, like, if it's passing, it's good enough. But to be on the safer side, like, this is a better way to do this. Like, of course, the powers, like, this is this, but this gives you precision errors for around, if you go to, like, very soon, this starts to give you precision errors. This thing, like, if you try to find 99 to the power 3, I don't know, or maybe 17 to the power 6. So this, like, the precision error will be not much. It will be around 1. Like, the value should be 19999.
I was getting this error, but in my Sublime only, like on online compiler, it was giving the correct output. But
Yes, yes.
in
So
my
it
Sublime,
depends on, like, computer to computer, compiler to compiler. So online, like, it may be giving you right for those test cases, but online also it can give you wrong for other values. So that's why, see, the it's like, we are we are iterating also for every possible value of x. So we can, that way, like, we can calculate during iteration only the powers, right? When we are first time iterating, we have 8 to the power 0. Next time we multiplied this val with 1, like, once with a, so we have 8 to the power 1, then we'll have 8 to the power 2, and we just need to check that val is less than or equals to L. We can use binary exponentiation also, but that too is also not required. But yes, we can do. And you have to make sure that when you're using binary exponentiation, don't calculate 100 to the power 17. You don't have modulo, and don't calculate these values, because you need to keep a check that the value that you're calculating, like, this is the, again, this is why that this way is, like, while iterating, if you're calculating the powers, you can keep a check like this. You don't have a modulo, right? In this, what binary exponentiation works best when you have, like, huge powers and you have a modulo value. Then binary exponentiation works best. And if you're getting TLE, then probably you had an implementation mistake. So I'll have to look at the code. Like if you're going up to, like, instead of 20, you're going up till 30, you shouldn't get TLE if your implementation is correct. So like probably you can raise a query and like tag me in it. I'll look at the implementation. Any other doubts? Okay, is this approach clear to everyone? Like just check for every possible value of x and y, and accordingly find all possible values for k. Okay, so let me show you the implementation. So this is the implementation. In this, I have first taken A, B, and L as input for each test case, and then this is my answer set. Like that will hold all the unique values of k, all the distinct values of k, and this val1 is nothing but my a to the power x, and val2 will be my b to the power y. So I'm iterating my x from 0 to 19, including 0 and 19, and my val1 needs to be less than or equals to L. Because if my val1, that is a to the power x itself, exceeds L, I cannot get a valid integer value for k. Same thing for val2. Val2 is my b to the power y. So I'm iterating my y from 0 to 19, and my val1 into val2. This is just long. Val1 into val2, and in between it's just long. You don't have to do this, because in this code also this is not required, because I've taken val1 and val2 both as long. This is required only when I'm multiplying integers. These both are long. So my val1 into val2 needs to be less than equals to L, and I'll increase my y. So first I'm checking that my val1 into val2 is like the product of this divides L. And if it's divided, if it is dividing L, I can insert the quotient of this division in my answer set. Finally, I'll multiply, like for each, like for next time, I need to increase my val2 by b. Like I'll multiply it again by b, so that it becomes b to the power 1 next. Then it will become b to the power 2, then b to the power 3 in this inside loop. And outside loop, I'll multiply my val1 with a. Finally, I can print my answer.size. Is it clear? Yes, no.
Yeah, clear, but how to think like that? I mean,
Okay,
my
so
all
like
understanding.
you are talking about the implementation.
Yeah, how do you approach to these kind of solutions?
Okay.
Like I was checking number of divisors and all.
Okay. Like I'll explain that. While true loop to find x. Yes, you can use while true also, and like you'll have to check that val1 finally needs to be less than L. Eventually, you'll get that condition only, that x doesn't exceed 20. Again, I'll have to check at like look at your code once. Just give me a second. I'm connecting my charger. Okay. So someone asked like how you can come up with these kinds of solutions. See, the first thing is the solution. Coming to the solution is one thing. See, if you look at the like, how did I come up with this kind of approaches? Just look at the constraints, and after that, you can just see that if you look at the constraints, you can just see that like a to the power x and b to the power y very soon exceed the value of L, right? And the second thing is the implementation. So Dev 3 teaches you like not just the like problem solving skills, but also how to implement these solutions in the best possible way. Like that is one thing that you can learn from div 3's approach. Like I think many people, that this is the reason many people get their solutions like hacked after the contest, during the online, like during the open hacking phase, because the solution that you have implemented, even though it's correct, but it is not like considering all the scenarios. In some scenarios it can give wrong answer. So that's why, like, probably if this would have been a dev 2, I would have also not implemented this solution like this. I would have also taken power. Why? Because like I know that in those we don't have open hacking phase, but it's like in those also we have like system tests. But in dev 3s there's a very high chance that the tests that are involved during the contest, those are weak. So that's why, like, I have learned also from these div 3s only, that it's always to be on safer side when you're implementing a SEO solution in a div 3 contest. Is it clear? Okay, so going to the next problem. In the next problem, we're given that in one move, like we are given again an array A. Okay, this is not the problem. This is the problem. So in this problem, we are given that we have an array A, and we need to determine whether it's possible to rearrange the elements of array A into some order, such that if we take, let's say the new order is B1, B2, Bn. If we take B1 mod 2, B2, B1 mod B2, B2 mod B3, so on till Bn, the value is non-zero. So let me show you one example. Let's say we have, let's take one example, 1, 2, 3, 4, 5, 6. In this, we don't have like we don't have to rearrange them in any new order. This is the correct order. If I take 1 modulo 2, then this will be passed to this modulo 3, then modulo 4, then modulo 5, and then modulo 6. So this thing will give me 1. This thing will give me again 1. 1 modulo 3 is 1. So all the way up till here, I'll have 1 modulo 6, and that thing will also give me 1. So I have the complete result of this thing non-zero. So this is what I have to see, that whether it's possible for me to rearrange the array in a order such that the final value that I'm getting here is non-zero. So see, the clever way to solve this is, first of all, just look, see what did I had here? I had a value 1, which was the minimum value, and that propagated till end. So if I have a minimum value, let's say if I keep my minimum value in front, and after that there is any value, A modulo B is always A if B is more than A, always, right? So irrespective of what is here, your minimum will be the final value of all the modulo after all the modulo operations. But this is only true when you have just one minimum value. If you have two minimum values, then if you keep like this, if you have the first value as this minimum, then after some time, this minimum will get like this minimum modulo minimum, and you'll get 0 at this point. And then this 0 will get propagated, because 0 modulo anything B is 0, right? Yes, no? But the point is, if you have just one minimum, like find the minimum value, and if it is occurring just once, if you have minimum values occurring just once, then the answer is always yes. We are not sure about the other case, but if there is just one minimum value, the answer is always yes, right? Okay. Now, if we have two minimums, what do we want? We again want, like after modulo, we want a value, we want something x modulo minimum, and we want to create a value which is less than this minimum, which is less than this value is less than this minimum. Because if this is true, I'll create my x in first place, my minimum in second place, and after this, the order doesn't matter. Why? Because I'll have a value after this modulo operation, I'll have a value which is minimum dash and which is less than this minimum. And then that value will get propagated till end. But the thing is there any x? See, if all the array, let's say this is my array element, these are my array elements, and this is my minimum. If my minimum divides everything here, then I don't have this thing because I'll have a 0 here only. Otherwise, there is at least one value of x for which x is not divisible by minimum. So x modulo minimum will always be less than minimum. Like a mod b is always less than b, right? Yes, no. So I just have to find an x for which x modulo x is not divisible by minimum. If this is true, I'll have my first element as x in new order, then minimum, and then after this, I'll get, like upon the modulo here, I'll get minimum dash, and that minimum dash is less than minimum. And the minimum element in this, like whatever minimum was repeating, right? So here there was some minimum, but now this minimum dash is less than everything which is here. So this will keep on getting propagated. So my answer in this case, if the minimum value is repeating, the answer is yes, if I'm able to find any x which is not divisible by minimum. Otherwise, if there is no such element, my answer will be no, because whatever you do, x like minimum divides every other element. So this means that the value that like minimum is kept anywhere, and before that there are many elements like you can keep in any order. Since minimum divides all of these, the modulo, the final value that you'll get up till here will be divisible by minimum. You will get 0 wherever you keep this minimum in your array. And plus, this minimum is occurring more than once. Is it making sense? Yes, no? If there are any doubts, you can ask me. Otherwise, we'll move to the implementation.
Can we do it with GCD also, using GCD?
Like how? I don't know. Like I haven't thought in that direction.
I
Like
seen
have
some
you?
solution using GCD after the contest. That's why I'm asking.
Like you saw a solution that was using GCD.
Yeah, after the contest, I saw my friends' submissions. They did it using GCD. That's why I'm asking.
Mm, there is a way, but like it will just complicate things. If I take, see, if in this, like the first thing is clear that if the minimum value is just occurring once, then the answer is yes. If in the second scenario, if I take my GCD of complete array, if it is x, then the answer is no. Otherwise, the answer is yes. You can say it like this also. This is basically if the GCD of complete thing is x, that is the minimum value, not x. This is minimum. If the GCD turns out to be the minimum thing, that is the minimum value. This simply means that this minimum divides every other element, right? You can do it like this also, but
Yes, yes, yes. Yeah, got it.
otherwise, if GCD is less than, otherwise GCD will be less only. GCD is less than the minimum, then your answer is yes. Otherwise, if GCD is equals to minimum, then your answer is no. Because in this case, minimum divides every element in your array. Is that clear? So it's the same thing. So okay,
Yes.
let me show you the implementation. So in this, I'm taking n as input, then I'm taking array A as input. Then I'm sorting it. Why? Like I don't have to sort it. I can just see that, okay, what is my minimum element? I can find the minimum using STL function, or I can sort it. So I have sorted it and I have checked if the first value is not equals to second value. This means, see, my first value is the minimum value. If it is not equals to the second, then it means that my minimum is occurring just once. So that is one benefit of finding, like sorting. Otherwise you'll have to do two things. First, find the minimum and then find the count of it. So if this is not equals to this simply means that my minimum occurs once. So if minimum is occurring once, I can simply print yes and continue. Otherwise, my minimum occurs twice. So I'm counting the number of elements that are not divisible by minimum. So I'll add 1 in if the current element, eth element, is not divisible by the minimum. If finally I have a positive value of f, that means there is at least one element that is not divisible by minimum. I'll print yes, otherwise no. Is it clear?
Is there any significance of adding into it? Like I
What?
can do na? Eh, like I can do it there if I get an element that is not divisible by minimum, then I break the loop. Is
Yes, you
there
can
any
break the
point
loop
of
here also. Yes, you can break the loop here.
okay?
If you're f, like if you find even once that there is an element, you can break the loop here. You don't have to go through the complete array. But in worst case, the time complexity will be still same, like big O of n. Because in your case also, it's quite possible that you were not able to find the element through the complete array, or you were able to find it, but at the last position. So breaking at a point, like seeing it time complexity wise, it will be same. Okay, so let's go to the next problem. So this is the next problem, and in this problem we're given that Isaac begins his training and there are n running tracks available. And the ith track, that is I is between 1 and n, consists of ai equal length sections. So given an integer u, that is between 1 and 10 to the power 9, finishing each section can increase Isaac's ability by a certain value, described as follows. Finishing first section gives Isaac u, second gives u minus 1, third gives Isaac's performance increases by u minus 2 upon finishing third section, and so forth. If Isaac finishes kth section, then his performance increases by u plus 1 minus k. So let me explain this problem first. Like, see, there are some tracks. Like each track, like there is an array, and this array has, like, there are n running tracks, and this has, let's say, 5, 4, 3. So there are 5 sections in this. This is 4 section. This track, like these are the tracks. Like the problem statement is very simple, but like it's complicated. Like it's just made complicated by the, like, a confusing story. So I'm just trying to simplify the story. See, and this is 3 sections. So these are n tracks, and each has these many sections, like AI sections, right? Now, if Isaac run through one section, if Isaac finishes one section, his performance increases by u. If he finishes 2 sections, his performance increases by u minus 1. If he finishes k sections, his performance increases by u minus k plus 1. Now, let's say you're given a query like, if you Isaac starts from this and this u is given to you, So how many sections, like what should be the R? What is the optimal R? You need to find what is the optimal R such that Isaac finishes every, like the total number of sections, total sections from L to R. Like this is the sections that Isaac will finish, and accordingly you're given a U, and you have to find what is this optimal R. See now how 543. Let's see how the value will change. If you had 543 S sections, and this was your L, and U was 10. So if this is my L, this was my R, this is, let's say this was my R. From L to R, how many sections did Isaac finish? 5. So for the first section he got 10, for the next section he got 9, for the next section he got 8. Then right. Then if let's say Isaac decided it up till here, this is the R. Then what is the total number of sections that Isaac finished? 9. So he'll get 10, 9, 8. Like this is the total increase in performance. This is my U. I'm always starting from U. U is 10. This is the value, right? So there are total 9 sections: 1, 2, 3, 4, 5, 6, 7, and 8. And for, if let's say this is my R, if let's say Isaac decided to choose R as this, then what is the total number of sections?
12. 12.
So this thing will come exactly like this, and you'll have plus 1 here, plus 0 here, and minus 1 here. Like let's take this as a little more, 4. So then you would have 13, and like this way this will continue, minus 2 will come. So you'll have 10 plus 9. This is your increase in performance, right? So here you'll have some value, here you'll get some value, and here you'll get some value. So out of all of these, you have to choose the most optimal. Like this, I think this will give you the maximum. So the R is this thing. So this is your answer. When your L is this value, L is 1. When your L is 1 and R is 10. L is 1 and U is 10. So in that case, your R needs to be 2. Because for R equals to 2, you're getting the maximum value, this thing. Is it making sense what we have to find? Like how we have to optimize R? Yes, no? Now, if we look at this thing, like we are given these are the track values. We have to optimize, like from here we'll start, and let's say from till here we'll L is this, R is this. So yes, so we have to find, like we need to get the maximum sum. So let's say there is X here, Y here, Z here, alpha, beta, gamma, delta. So, and there is, I have a U. So up till a point, see, if you look at this, up till a point your values are up till a point your values are increasing, and after a point your values start decreasing. So till where your values are increasing, 10, 2, then plus 1, then you'll get plus 0, and then after this point your values are decreasing. So basically for the next, like how many sections, like basically how many sections, at max 10 sections. So running 10 sections is will give you positive, and after that you'll get 1, 0, and then you'll get all the negative contribution, negative performance for running more over more sections, right? So basically this U 10 is nothing but U. So what I'm trying to say, you need to run, if you want to get the maximum value, like the most optimal value, you need to run maximum, like run U sections. U sections to get the most optimal value. And here, if you run up till here, you'll get X plus Y these many sections. If you go till here, you'll get these many sections, right? Up till U sections, your performance is increasing, and after that, it will decrease. Is it, like, are you understanding? Yes, no? Okay. So if I'm at this point, and you have to find what is the first R which will give me a value which is more than which is more than or equals to C at this. If I calculate C, there are two ways to do this. I'll explain both. The first way is, if I calculate prefix sums, I just need to find from this point the, like, what is the first R up till which I'll get, what is the closest R up till which I'll get the total of this either less or equals to, like, U, right? Like, what is the closest value, like what is the closest R for which I'm getting the sum closest to U, because I want to run maximum, like I want to run as close as to U sections, because at exactly U I'm getting the maximum performance increase. So one way to do this is, like, yes, in some cases we will be able to take, like, instead of running up till R, we can run up till R minus 1. But because, but that's something like that. I'll come to that in a moment. But the first thing is how to find this R. So if I take prefix sum, my prefix sum array will be strictly increasing. And at this point, I have some, let's say prefix sum as something L. So I just need to find some prefix sum R for which my sum R is either more, like what is the first smallest sum R for which this is sum R is more than or equals to sum L. So how can we find this? How can we find this R? Using lower bound, right? Binary search, basically. Find the first R for which sum R is more than or equals to sum L plus U. So that is the first R for which sum R is more than or equals to sum of prefix sum of L plus U. Basically, this will give you sum L, sum R minus sum L is more than or equals to U. Basically, this is also sum at prefix sum at R minus prefix sum at L is more than or equals to U. So this is the first R for which we're getting the range, sum of this range more than or equals to U, right? There is no point in going beyond this because it will contribute in negative only. This is the first R for which you got the sum of the range values as more than or equals to U, right? Yes, no. Is this thing clear up till now? Using binary search, we can get this. Okay. Basically, this is lower bound. Find the first R for which the value of prefix sum is more than or equals to sum L plus U. Now the thing is, it's quite possible that this sum R is way more than what we wanted. Like, it's quite possible that the prefix sum here was 10 and here we are getting 100. And sum L, sum at this point is 1 and U was 15. So we searched like we found lower bound of 16. Sum of L plus U, that is 16. We found lower bound of 16 and we got this thing, this value. But this is way more than, see, U is 15, so we started from 15 plus 14 and got 0 at this this thing. Like, up till here the sum was 10. So till here we could have got this thing, but if we go up till 100, if this is the total number of section, like this means up till here we have total 100 sections that we will, like, that Isaac will run. So this will go -1, then -2, then -3, and way more. So even though this is the first value of R, that is for which sum at L plus U is less than or equals to, like, sum at R is more than this, it's better to also check that what happens at R minus 1. At R minus 1, one thing is sure, that sum at R minus 1 is less than sum at, because this is the first value which was for this which it was more. So sum at R minus 1 is less than sum at L, prefix sum at L plus U. But we can check at R minus 1 also, that because it's possible that this value is contributing way more in negative than we are getting positive from this. So it's better that we stop at this only and consider this as our answer. So just check at R and R minus 1. Is it making sense? Just do. So R is the first value that at which sum at R, prefix sum at R is more than prefix sum at L plus U. So basically, this means that the sum of this range from L to R is more than or equals to U, and then just check at the previous value also. And why we are doing this? Because we need to run as close as possible to U sections. Why? Because only up till U sections we'll be getting positive value. After that, we'll be getting negatives, negative performance. Another way to do this is C. Like I won't explain this one in much detail, but if you want the implementation, I have the implementation also. I can share it with you guys. So like this is the easier implementation. Just apply lower bound and check. The another implementation is C. Like I have taught this in class also. Up till a point, your value will be increasing, and then you'll start to get negative contribution. So what is this? This is your L. You'll be getting U, then you'll be getting U minus 1 added, then you'll be getting U minus 2 added. After some point, you'll get 0 added, then minus 1 added, minus 2 added, minus 3 added. So this is how your performance value will get changed. What is this?
Convex function.
Yes, like to be precise, this is a parabola. And you cannot directly apply binary search on this, but you can apply. You cannot apply directly. This is a parabola. You cannot directly apply binary search on this, but you can apply ternary search. Like you have to find this position. What does this R? You don't have to find the value here, but you have to find the R. What is the R here at which you're getting maximum performance? So what you can do, you can apply ternary search. So in ternary search, we just divide our range in 3 parts and find value at mid 1 and mid 2. So I've explained this in class. But this way, the implementation will be 3 times, not 3 times, at least 2 times complex than what it will be in this thing. Just fine. And we are doing the same thing. Like, but we are actually looking at the function that we are getting from this thing. Like the function that we'll get from these u plus u minus 1 plus u minus 2. So this is the function that we'll get. And on that function, we are trying to get the point of maximum. So instead, we can do it like this also. Is it clear? Like, don't worry if in your class this is not covered. If in your level this thing is not covered, it's completely okay. Okay, so let me show you the implementation. So this is the implementation. In this, I have first taken n as input, then I have calculated, like while taking n as input, like all the values, I don't want the values, I am just calculated prefix sum at this point only. Then, and in my this, I have taken array global. So I am starting from 1, not 0. Like usually we start from indexes 0. Right? I'm starting from 1 and I have calculating prefix sum. And sum of 0, by the way, is sum, like when I'm at 1, this will be sum of 1 is equals to sum of 0 plus x. Since this is a global array, sum of 0 will be 0. I don't have to initialize it. For all the global arrays, they are initialized to 0. Like all the values are initialized to 0. Then for every query, just take like what is L, what is U. I have to find lower bound of U plus sum of L minus 1. Why L minus 1? Because whatever the sum was, like if you have to find a sum of, let's say I have prefix sum of this range, prefix sum. If you have to find sum of this thing from L to R, what is the sum of this range? It is prefix sum of R minus prefix sum of L minus 1, right? Is anyone having any doubt in this? L minus 1. This thing, like if you subtract this part from this part, you'll get the sum of this part. So that is why lower bound of, like while I was explaining, I was writing sum of L plus U, but it would be sum of L minus 1 U. Sum of L minus 1 plus U. So this is what I am finding lower bound of in my array. So this is like, this will give me address and I'm subtracting the starting pointer from this. So this is my R, the first R at which my sum at R is more than U plus sum of L minus 1 at L minus 1. Now I'm checking the previous one also. Why? If like I said, it is better, it is like we can get a better answer at that place also. So just check if sum of at this answer, which is this R minus U, is more than U minus sum of previous. Like this is nothing but like this is I would have written like sum of L minus 1 on both sides also. Like what is the value that you're getting? See how many tracks are coming on this side. Like from L to R, you'll get sum of R minus sum of L minus 1. And if you went up till R minus 1, how many tracks will you get? Sum of R minus 1 minus sum of L minus 1. Is anyone having any doubt in this? Like this is the number of tracks if you go from L to R or L to R minus 1, right? Now, if you decide that, okay, you can stop one before. So either doing it like complicated way, what you can also do is, this is your total number of tracks and this is your total number of tracks here. So you can do two things here. If you don't want to complicate things, just find for this, just find total. Like total will be, let's say, X. Like let's say total is total like this thing, and you have U. So definitely total will be more than less than U in this. Why? And then this total will be more than or equals to U, right? Because R is the first value for which this thing is more than or equals to U. So that's why this thing is total. Total is more than equals to U. Total is less than U. So you can do two things. Just use basic maths, and you have to find. Just give me a second. You have to find total. You have to find, in this case, if total is less than U, you have to find total plus total minus 1 plus total minus 2, and these should be U terms. You have to find this. No, I have written wrong. I have like, you have to find U plus U minus 1 plus U minus 2, and you are running total number of tracks. Like Isaac is running total number of tracks. So this is the performance increase in this way. Like how can you find this? You can find this. What is the sum of arithmetic progression? 1 plus 2 plus 3 all the way up till n. This is nothing but 1 n into n plus 1 by 2. This is an arithmetic progression, AP, right? So if you find AP up till U, like what is the sum of AP? That is going up till U, that is. And from this, like you need to just go up till total. So this total number of terms. So that is the last term will be what? U minus total plus 1. This is the last term. And the next term will be U minus total. You need to subtract whatever is coming after this up till 1. So just subtract x into x plus 1 by 2, and this x is nothing but x is U minus total. So this way you can get the sum of this series, right? The performance increase in case you stopped at R minus 1, right? Yes, no. Is it making sense? Like I'm just like, if you don't want to use any mathematics at this point, you can do it like this also. Same way here, total is more than U. So some terms up till like 1, everything will come. So first find sum of first U arithmetic progression terms. And from this, since from U you started U minus 1 plus U minus 2, you went up till 0 and then you went backwards, minus 1, minus 2. So how many terms will these be? So up till here there are U terms, there's a 0 here, And then after that, there are these extra terms. So this is total minus u. These are the u terms minus 1. So again, minus this x into x plus 1 by 2. And this x is this thing. These are the negative terms, like you can 1, 2, 3 in negative. So find this thing. And if this is maximum, then go up till r. If this is maximum, go up till r minus 1. Is it clear? Is it making sense? Like this is the best way to like visualize this thing. If you like simplify these terms, see, sum of L minus 1 is coming on both sides. You just have to check. This is u, this is u. And if you like optimize these two terms, these two, you'll eventually get this equality, this kind of equality. But like even if you are like stuck with maths, you can just calculate, like this is the sum of arithmetic progressions. Like just calculate this thing, just calculate this thing. You have to calculate these in long, and eventually you'll get the sum of this part and this part. So this is when you're going up till r, this is when you're going up till r minus 1. And whichever is maximum is your final position till which value you will go. Finally, make sure that you are between 1 and m, like L and m. Why? Because see, like lower bound can give you like something after n also. In case this value is more than like u plus sum of L minus 1 was more than the final value of prefix sum. In that case, you'll get lower bound, like because we are trying to find the first r is nothing but the first position at which sum of r is more than or equals to this thing, right? U plus sum of L minus 1. But what if there is no value in sum which is more than this thing? In that case, your r will be pointing to n plus 1. So make sure that you correct this. Finally, we can print our answer. Is it clear? So this way, it's very simple to implement. Any doubts on this? Yes, no, no doubt. Okay. So that's it, yeah. Thanks for joining. Bye bye.